So give you 2 more days, and I think give you on Sunday, I think still 1 p.m. You can check on the Blackboard. And the Monday, and after due on Sunday, I will right away to post the solutions. Otherwise, drop the emails if I would forget it. And Monday next week, we have the second test. And the contents just on this chapter 3 only. Nice. Okay, and some of the problems on homework, chapter 3, a little bit challenging, and I will do probably one today for demonstrations. And I can tell you there's a couple questions on Monday, and one of the questions will be gear set, because that is a very important comes to the problem. So for sure, you better to exercise and know all the concept. And today I will go over a few problems as many as possible I could about the gear set. And pretty much we almost finished chapter 3 today. And here this is the one problem about the second type, indeterminate problems of this second type, and I didn't do it Monday, right? I didn't finish, so I tried to finish this problem. And I believe I have written the problem statement last time, and so pretty much you can turn over your lecture notes. So for this one, basically this is a composite shaft, and assuming they grew so well, there's no relative displacement between each others. And we apply the torque T, and T will be in some way to distribute. A portion of the T will go to the sleeve, and the other portion will go to the core. Everything will be in static equilibrium, and this one will be under the static equilibrium. So the compatibility equation for this one will be the twisting angle of the twist of the sleeve and the core. They should be equal. So for this one, we have to determine some information, and let me fill out the screen and work on here directly. And again, probably you already have the statement been written down in your lecture notes last week. I didn't finish. So for this one, this is indeterminate problems, and say here we take the free body diagram. One is on the sleeve. And assume his portion took from the applied is called the T sleeve, we call it TS. And the other portion is for the core material, and its portion is shared is called the TC, core. And by equilibrium, we know that T is the torque we applied must be equal to TS plus TC. So that is the equilibrium equations. And here we've given the information carefully. So here this is CI, CO, CI is equal to 0.02 meter, CO is equal to 0.025 meter. So here, therefore, the polar of moment of inertia for the sleeve, that is pi over 2 CI. Let me get all the information ready before we explore these questions. So that one is 3.62 times 10 to the minus 7. And for this one, the C equal to 0.02 meters, so the J equal to pi over 2 C to the 4th. Okay, so those are the basic informations. And now we don't know the value of the TCTS, but we try to find. And compatibility equation is this. They both will rotate at the same angles, so that means the twist angle phi S must be equal to phi C. And this is our compatibility. Okay, so from here we can try to get some information. Here for phi S will be equal to TL over GJ. And for all the information we pick up for the sleeve. Okay, that means the length, rigidity modulus, and the polar moment of inertia and the torque. So for example, here the T should be TS. And here for T of the core, TL over GJ, and that is take up the core's informations. And the Q values must be equal. So here we set it up the phi over L, because this composite material has the same length. So this will be equal to TB GJTS will be equal to TC GJC. Okay. So therefore, from here we should be able to find the informations. And for example, here let me stop and a little bit to look at the problem statement. So basically, for these questions, here the T we are given in total is 600 Newton meters. We want to determine the maximum shear stress in the jacket, in the sleeve, and then the maximum shear stress in the core, and the angle of the twist. So basically here, as long as we can solve for TS, TC, those questions should be solved right away. So so here, before we, basically here you can see, right now we have how many equations? We have these equations, and we have these equations, 1 and 2. So for 2 equations, we have 2 unknowns, so we should be able to solve for TS and TC. So here, one way is using equation 1 and 2, we can solve for TS and TC. And here I want to show you the different way to do it, and maybe you can save a little bit calculation rigors, is this. On the other side is this. By equation 1, we can obtain is TS equal to phi L times GJS, and TC equal to phi L times GJC. Okay, simply I just remove the denominator of each term to multiply to this term. Okay, get this one. So from here we know that the 600 equal to TS plus TC. So basically the 2 terms multiply as take summations times GS plus JC. Okay. So here we know the L, we know the G, we know the J, and J is JC. So here we can calculate, for example, phi over L, this number will be equal to 17.9 times 10 to the minus 3, and this should be radian per second. So I calculate this number pretty much there, and then therefore for the questions, the maximum stress in the sleeve, and that is T C over J. wait a minute. Here we can calculate this. The maximum is TC over J. And this one, we try to utilize this information. We can try is this. We know that the phi equal to TL over GJ. So from this equation, phi divided by L equal to T over GJ. So therefore, from here you can see if we can further do it, T over J here, because we have information T over J here. So I try to come up with that number, G times phi over L. So using this information, I plug in this information here. So that is G phi L times C. Will that be okay? Yes?
In the middle part on the left, how did you just factor out G when they're two separate values?
Yes. For example, here, I use the two equations. I come to here, this form. Okay, and on the other side, I use this and this, and I come to the second description. Okay?
Right.
G is different for the brass and the steel, though.
Yes. So here, let me label it. So this will be the S, this will be C. We just plug in the individual values for calculations.
So the one below it, the 600 is equal.
That should be, oh, yes. So that should be, yes, thank you. GS, JS, GC, JC. Thank you. Okay, so therefore, using these equations here, the maximum, the tau maximum in sleep will be equal to this one, G times phi over L times C. For the sleep, this is a sleep, so the maximum will be at the outer here, so we take the CO, right? Okay, we take the outermost, the radius. So this number will be equal to, we simply plug in 39 times 10 to the 9 and times 17.9 times 10 to the minus 3. And CO is 0.025. So this will give us a 17.5 MPa. Okay, and let me iterate this part. We will continue. And then the maximum in core, we plug in the information here is 70.2 times 10 to the 9th and times, let me repeat, that is G C times phi over L times C. Okay, so that is 70.2 times 10 to the 9th times 17.9 times 10 to the minus 3 times 0.02. Okay. And then the angle of the twist, that is very straightforward. Basically, we have calculated this number, simply multiply with L. So that is 17.9 times the minus 3. And that is radian per meter. And multiply with the 3. That's the length of the meter, the length of the shaft. Okay? So, I think this approach, or either you directly solve for the two equations, that should do the work. Yes?
Is it L 2 meters?
L is 2, yes. Thank you. Any question about this exercise? This is an example. And for those of you who are late, a little bit late here, and I just announced before you came, Friday our homework 3 for chapter 3 extended to Sunday, 1 p.m. This is the first one. The second one, on the coming Monday, we have a test on this chapter. And there's a multiple questions, but that should be enough for 1 hour testing. And if no questions, then we move on to other exercise. This one, let me. This one is somehow similar to one of your homework problems. And the statement of this question is this. We have, so basically the gear set, and then this problem must be in balance. So you could imagine is this. And right now at this moment, I don't know which is driven, which is the driving, which is the input, which is the output. It really doesn't matter. For example, here, if this would be the input here, so if this apply the torque here to make the gear rotating in this way, so that means the gear of the top will be rotating in this way. So to get an imbalance of the whole system, this must be logging in that direction. If you can play a little bit around this system, if the two values, TF, TC in certain values, the system must be imbalanced and no movement. And once they get imbalanced, the only thing is that both shafts will be strained, which will be deformed a little bit. Okay, so for this question, basically we apply the two torsions and to log in this gear set. And for this specific applications, then here we have all the informations. And here we want to know is, okay, the allowable shear stress is 7 KSI. So that means for both of the shafts, the maximum shear stress shouldn't exceed the 7,000 PSI. Using that criteria, we're going to find out what is the appropriate value of the TC here. Or vice versa, if we will know the TC, this must be imbalanced. We can also calculate the TF. But for this question, we find the TC. Okay, so how to solve for these problems? And let me turn on this one. For this case, the thinking process is the first one. We need to find out what is the relation between the two torques. Okay, the relation of the two torques basically is governed by the gear set. Then the second thinking is, once we know the relations of the torque in individual shafts, then we can formulate the maximum stress, and which just constrain the maximum stress under the allowable. So with the two informations, we should be able to solve for these problems. And again, the maximum stress in both shafts must less than or equal to 7,000. So for this case, we have to check the both shafts individually. So here we're starting from, so two things. One is the maximum stress is less than 7,000. The second one is the relation between the two torques. So we apply the two things individually. First one, the maximum on one side is TC over J, and that is our generic formulas. And we plug in individual informations. Okay, so this one is less than or equal to 7,000 PSI. So we keep this in mind. And we have to apply information individually to each shaft so that the number of the C and J could be changed from one shaft to the other. And so now we and the relation and between the TC and TF is this. Look at here. So